So the last section we're going to go through is 12.5, which is about the normal curve. So really what we're going to be doing is kind of working with histograms. We've seen how to create them, and we know they display information about a data set. But the particular shape that histogram has can tell us a lot of information about what's going on. So we have a few common shapes that will occur based on certain real-life scenarios. So the first one is called our rectangular distribution. So all that means is the shape of the graph is going to be like a rectangle. So when you look at that histogram and you have your data values on the bottom, these would be those midpoints or mid-ranges. And then you look at the frequency of each, it's going to form a rectangle because all of the observed data values will occur at the same frequency. So this really means everything is equally likely to happen. So if you want a realistic example of what kind of data could have this, you can think about rolling a die. So when you roll a die many times, everything has that equal chance. So you'd assume that each single data value is going to occur at the same frequency as the other. Okay. The next shape we have is a J-shaped because it's going to be constantly increasing or constantly decreasing. So overall, there's this kind of arching J over top. It's not quite a J, but it's close to it. Or it's going to constantly be decreasing. So J-state distributions, they have to be doing one or the other. I can't suddenly have another one that's up here. That would be a completely different shape. So if you want to think of a realistic example of something that will have this, if you count the number of hours people study per week, it's probably going to have a similar shape to this one. So it's likely they're studying like 1 to 4 hours, then it drops off 4 to 8 hours, then it drops off, and there are less people studying those higher values. Okay. The next one is called a bimodal. So we learned about bimodal last time. So in all of these graphs, you're able to easily see what the mode is because it's the one that appears the most. So in here, there is no mode because everything is exactly the same. Bimodal is when you have two different modes. So you're basically going to have two different peaks in your graph. So they have to be non-adjacent. If they're occurring next to each other, that's not going to be considered bimodal. So you see there's two that are not next to each other because there's these other two data ranges in between. And they're appearing more frequently than the other. They don't have to necessarily be the same frequency, they're just clearly more than the others. So if you want a realistic scenario, think about heights of men and women. There's a different average height for men than there is for women. So you're likely going to have two frequencies that occur more often than others. One peak will be for the men's average height, one peak would be for the women's average height. Okay. Now the next one is a skewed distribution. So it's going to be backwards to your intuition in terms of the naming. So what that means is you have data that's skewed to one side. So I've got some other values that occur down here, but most of the data is falling in this range. Or it could happen the other way. Most of the data is going to occur over here, and then you have a couple little bit at the beginning. So the skewing is backwards to the naming. You would think that this particular instance is going to be skewed to the left because most of the data is on the left, but it's really skewed to the right. And then here, your tail end is on the left-hand side, which is why it's called skewed to the left. So the tail indicates the direction of it. So you're going to have one longer portion that occurs less frequently. So a realistic example, if you think about number of kids in a family, a lot of people have 0 to 4 kids, but then you have others that will have 10, 11, 12, a ton of kids. So in that case, you're going to have a bunch of tail ends over here. So the nice thing about this is, again, you can immediately tell where that mode is going to be in each of the data sets because it's the highest peak of it. you can also know what the median is going to be. So like here, this would be our mode. This would be our mode. Okay. Now, because you have these few data points that are kind of outliers, so there's a lot of really large values here, they're going to push that mean to be closer to the tail end. So the mean's going to occur towards the tail side. On this particular example, the tail end's over here, so the mean's going to be closer to the tail end because those few outliers will have a heavy impact on the average. Most of the time, the median is going to occur between these, so it follows a particular order: mode, median, mean. And then in the skewed to the left, it would be mean, median, mode. But that's not always the case. There are certain circumstances where that median might flip, but the mode and mean will stay consistent. Okay. Now, the very last type of distribution that we're going to go over more in detail is called normal, because it's the one that most data is going to follow. It's normal, or the most average. So what happens is that data is going to be really symmetric. You have that most, which is our mode. It's also going to be the median. So they all are going to occur, all the central tendencies are going to be exactly the same. So this is called the normal or Gaussian distribution. So it's symmetric about the mean. So this shape we have is going to be a normal curve. And it's going to be bell-shaped. So if you were to kind of outline all of the data points, it's going to look like a bell. And it is symmetric about that center point. And the great thing is the mean, median, and mode are all going to be exactly the same for the normal distribution. On top of that, we can actually know about where the data is going to lie. So if we have our bottom part of our histogram and our mean goes directly in the center, which is also the median and the mode. But for now, we'll just put the mean down here. Your curve is going to be bell-shaped and it's symmetric about the mean. So you get exactly the same shape on both sides. We have something that's called a standard deviation where you branch off from the mean. So if I go over this one standard deviation on each side, this distance is going to be a standard deviation. And in this case, it's a single one. The great thing is, between these two values branching off one standard deviation on each side, 68% of the data is going to lie within these two values. Okay? So 68% of the data lies within this one standard deviation. If you go out another standard deviation, so it would be the same length. So this would be 2 standard deviations. Then, between these values, 95% of your data will lie within this range. And then finally, if you go out one more standard deviation, so same distance out, this will be 3 standard deviations, this will be 3 standard deviations. Then the majority of your data is going to lie in here. It's going to be 99.7% of the data. So everything is going to occur close to the center. If you go out a 4 standard deviation, it would be like 99.8 or 99.9. But there's not many that are going to lie very far from this central tendency measure. So let's just look at a specific example. Annual daycare cost per child is normally distributed with a mean of 8,000 and a standard deviation of 1,500. So what that means is if we look at our child care, 8,000 is our average. It's directly in the middle. If you go out a single standard deviation in each direction, this distance is going to be 1,500, and then it's going to be another 1,500. So that is a single standard deviation. Okay, and the notation we have for it is this letter sigma, but you don't have to worry about that too much. Just know this is a single standard deviation. So if you go out 1,500, this would be 9,500, and this would be 6,500. Okay. So what that tells us is that 68% of people pay between $6,500 and $9,500, because 68% of the data is going to lie within this range of 1 standard deviation. Now if you go out another standard deviation, so you go out 1,500 more in each direction, this will have been 2 standard deviations. And the actual cost then, 9,500 plus 15 will be 11,000. And then the 6,500 minus 1,500, this will be 5,000. So between these two data points, 95% of the people will have paid within this range. So now 95% of people pay between $5,000 and $11,000 for childcare. And then if we go even further and go out a 3rd standard deviation, so you go out 1,500, go out 1,500. So these two values will be 3 standard deviations, 3 standard deviations. If you add 1,500, this would end at 12,500. Subtract 1,500 from here, you get 3,500. So now between these two values, 99.7% of your data will lie. So 99.7% of people pay between $3,500 and not $11,000, it's the $12,500 on childcare.